and the problem solving. But that is the agenda for the day. Any questions about the schedule or what we have going on today or in the near future? All right, just so I don't forget to tell you guys in person, and then for those that come tomorrow, or B day, I guess I won't be any of you guys, it's just gold B. So, but on the, when you're in class, I've got all the handouts for all the things we'll be doing next week as well. So, and you guys haven't had a chance to pick up worksheet 1 yet, so you can grab that. Plus there's 2, 3, and 4, which is what we're gonna focus on next week. The worksheets will primarily for this part of the unit be things we do in class, not so much assignments. So the assignments will usually be something else like a Gizmo or positive physics, and in class we'll be kind of wrestling through lots of example problems. Today's really the kind of the last day of notes. If we have quote unquote notes in future days next week, it's mostly focusing in on, okay, here's a new kind of problem, let's talk it through, not really notes on new concepts. For uniform circular motion, once we learn about forces today, you pretty much know everything you need to know about UCM. It's just a matter of, okay, now here's all these different kinds of problems they could ask you and how you need to think them through. But first, let's go to the intro worksheet. So I'll stop sharing this and we'll just have students kind of take turns giving the work and the answers. So if you are selected, make sure that you are prepared to show the work as well. So we'll start with number 1, part A. Sally, could you get us rolling with number 1, part A and demonstrate how you solve that for the intro worksheet?
Yeah, is there a way that I can like draw it? How do I show the?
On the share screen tab at the bottom, there's a whiteboard option.
Oh, I see. Okay. All right.
Got it.
Okay. So for number 1, it's asking for the frequency. So we can use F equals 1 over the period. And we know that the period is for 4 seconds. And then that would give us 0.25 hertz.
All right, very good. And we do want to rewrite it as decimal so that it shows sig figs. And the numbers that we're given that are dependent in this question, which is really just the 4 seconds, has 2. So our answer here should have 2 like it does. Good. Any questions on 1A? All right, we'll stick in the Zoom for the rest of number 1. Kyle, can you talk to us about 1B?
Yeah. Whiteboard. All right, so since asking for velocity, so it'd be, I did V equals the 2 pi RF, and then when you substitute that in, it's V equals 2 pi, then the radius is 1, and then we have the frequency at 0.25, so then that equals 0.5 pi, which equals 1.6 meters per second.
Yeah, leave it on the screen there for a little bit so if people are checking the work, they can follow that through. But yeah, that looks good. You could also use the V equals 2 pi r over T form of that equation and use the 4 seconds that was given in the original problem. You get the same answer. So if you may have done it a different way. And that's one thing you're going to learn more and more and more as we go through this semester is every kind of new problem we learn, there's not just one path. There's generally lots of different paths. Here, there's probably only 2 real clear paths, but the more information we gain and the more knowledge we gain, the more tools in our physics tool belt, the more paths to victory. All right, thank you, Kyle.
Mr. Webb,
Yeah.
I forgot my sheet, so can I just take notes on this and then check it when I get
Yeah,
home,
there's a
or is
couple
there-
extra copies right in the far right, 3rd one up. Yep.
I'll just check what I have at home and
Okay,
then.
all right, Johnny, how about 1C?
Okay. So for C, it's asking for the acceleration. So I used, let me see if I can draw this. A equals V squared over R. And then in the last problem, Kyle found that the velocity was 1.6 meters per second. So I'll draw that 0.6 meters per second, and then squared. And then R for the radius here is 1.0 meters. And then that's equivalent to, let me just make sure I put it right here. So that would be 2.56 meters per second squared.
All right,
Or with
little-
sig figs, 2.6 meters per second squared.
yeah, good. So sig figs, go to 2.6. Good, I'm glad you mentioned that. And depending on your setup and how you rounded, if you used the 1.6 as rounded, I think you do get closer to 2.6. If you're on your TI Inspire, just going up, like arrow up and highlight the velocity and then just plug that whole thing in unrounded, I think it comes out closer to 2.5.
Yeah, I got 2.47.
Yeah. So those small variations are fine as long as you only have the 2 sig figs in your final answer and you got the correct unit and you've showed how you set the problem. So they don't, like when significant figures and rounding is part of the rubric grade, there's flexibility in that last digit, because remember that last digit is an estimate anyway and a measurement. So, all right, very good. Thank you, Johnny. For number 2, let's switch gears here to the classroom. So Evan, why don't you show us how you did number 2, part A, and I'll follow you here on the laptop.
On the whiteboard or?
Yeah, just pick a spot on the whiteboard, I'll follow you. I'm just gonna turn this video on. There we go. And it, I think if you go to speaker view, you should be able to see, so there's I'm gonna go back here so it's not so much glare.
It was asking for the period. So I use T equals 1 over the frequency. And then I just plugged in 25. And I actually didn't put into decimals, but it would be like 0.04. Yeah.
So how would we make that show 2 sig figs?
0, I guess.
All right. And that's one of those tricky sig fig rules that I just wanted to review here. Zeros in front of a number are not significant. So those leading zeros at the beginning of the number are not significant, but the zeros at the end of a number are significant if there's a written decimal. And this has a written decimal, so the trailing 0 is significant. So the zeros in front are never significant, but trailing ones are if there's a written decimal. So that one looks good for part A. Ethan, you want to show us part B?
Wanted the velocity, so we do E equals 2 pi r over t. So we have t and we have the radius, so it's v equals 2 pi times 5.0 meters over 0.040 seconds, which equals 785.4
with sig fig, that's too many squiggles. Sig figs is 790.
All right, that's good. So I'm just kind of a little bit closer so we can see that well. Any questions about A or B for number 2? We're definitely seeing a pattern here. We're just kind of using the same equations over and over. A was a little different because I wanted period instead of frequency, but this is basically the same exact thing we did in number 1B using, he used the 2 pi r over t format, as I think Kyle in the previous one did 2 pi r f, but equivalent forms of that equation. All right, good. For part C, let me pause this video here. Don't want to make you seasick moving around too much. For part C, I don't think we'll show the work because it's basically the same thing you would do for number 1. Just use v squared over r. But Cade, what did you get for 2C?
Sorry, I currently can't find the worksheet. I finished it, but I can't find it anywhere in my
Okay, keep
papers.
looking. If not, you can download another copy. Andy, how about you? What'd you get for 2C? I think you're still muted.
Yeah,
Yeah,
I gotta be honest, I also can't find mine. So, yeah.
All right, moving on. Nat, do you have it? Aiden?
Yeah, I did 790 meters per second for C, right?
Yeah.
So yeah, so I did 790 meters per second over 5, and I got, I don't know if I'm right, but 120,000 meters
Yep.
per second squared. Yeah, okay,
Yeah, that's correct.
that's what I
when
got.
you yeah, when you get that big a number, sometimes it's like, is that right?
Yeah,
right?
it seems like a large acceleration.
Yeah. So that means every second it's changing by 120,000 meters per second. That's a really high acceleration. But if we stop and think about the numbers given, part A, or sorry, in the description, we've got a 15 kilogram mass. So that's an over 30 pound object, right? Pretty heavy. And it's at a radius of 5 meters. So that's like a 30,
15 feet.
yeah, that's a 18 feet of radius, over 30 feet, 36, 37 feet of diameter circle, huge circle. And then it's moving at 25 hertz, meaning it's going around that 35, 36 foot circle 25 times every second. So it would take a lot of force to get a 30 plus pound object going 25 times per second around a 30 some foot diameter, right? That's why the acceleration is so massive. And one of the things you're hopefully noticing here, do you need the mass in any of these calculations?
No.
No. So really the mass is a distractor in some ways mathematically. It's just thrown in there, but it can give you some context. Like for this one, we can say, oh, that's really big. It would take a lot of force to make that turn, like even if it wasn't going 25 times per second, and it wasn't a 30 plus foot, circle. Even at a small circle, swinging a 30 plus pound object would be hard, right? And so that would take a lot of force, which means it's going to have a large acceleration. All right. Questions on 1 or 2? All right. I think for the second page, I'm just going to show the work real quick, and you can kind of check your answers, and we'll see if you have any questions. So let me get that here. I don't think I have that one open yet, but there we go. Oh, no, that's not it.
Screenshot.
Yeah, that one's already open.
Whoops.
There we go. Yeah, the one I opened was already open, so I'm not sure why it opened again. I probably have 2 copies of it open now.
I think it just.
Oh, no, it just opened. Yeah, okay. That's what it started to wonder. It took so long. I was wondering why. All right, so if we go to the second page, for part A, what is the frequency of the rotation? So we got a radius of 2 meters and a period of 10.0 seconds. So actually we need another 0 on here for sig figs. If we just take the reciprocal of that period, then we should get 0.100 hertz. Since the seconds is all that matters and it has 3 sig figs, even though the 2 meters only has 2, that's not applicable in this problem at this step. And the 0.5 kilograms only has 1 sig fig, but that isn't a part of any of these steps. So for step A, we don't need to think about those numbers. For part B, what's the velocity? So you could use either method here. You could change or use this frequency that we've calculated, or we could use the period that was given. And either way, we're going to have 2 sig figs because of the 2 meter value, and we're going to get roughly 1.3 meters per second. And then for part C, the same thing we've been doing. So parts B and part C on this one are pretty repetitive because you're just practicing using the same equations over and over, depending on which form of this velocity when you use. And for acceleration, we're just going to use v squared over r. We just found the v squared. I think when I typed it in, I must have just copied it or something. That 1.3 must be 1.26 something.
Yeah.
But if we want to show sig figs, probably better to just show 1.3. But again, if you on your calculator, if you don't use the round number, if you use the unrounded version by arrowing up and highlighting it, that won't give you a wrong answer according to College Board. Because you could always, in a multi-step problem, you could always integrate these equations together and make it one equation. And so they're going to say whether you round it midstream or not, they're not going to penalize you for that. Because some students might need to do it in multiple steps. Some students might combine the equations into one step and never need to round until their answer. So they give some flexibility there. Yeah, so that is number 3. Any questions about number 3? So I think actually if you do round it, you might get 0.80, I forget, but it's going to be pretty close to that. And then for number 4, so you got a 500 kilogram mass spun in a circle of 25 meters with a velocity of 250 meters per second. So another pretty impressive object here. To find the period, this one's a little different. So the first one's all gave us frequency or period, so we could just use the reciprocal, but this one doesn't. It gives us a little bit different information. So we're switching the order of things that we're doing, but still we're using the same equation. So to find the period, we could use that equation that says the velocity is 2 pi r over the period and just solve for t. It's given that the velocity is 200 meters per second. 2 and pi are constants, and then it's got a radius of 25. So we just plug those in and solve for t, and it's about 0.63. Now, if you do it as a 2-step problem and you round off, I think it might end up coming up 0.62, if I remember right. But this would just be in one step. So some students actually would use the other velocity with the frequency, find the frequency, and then go from there to convert it to period. And that's fine. It just takes 2 steps instead of 1 if you do that. And then so some students actually found B basically first, and then found A. And that either way works. But I used the answer from A to answer B. So knowing for the first part. So knowing frequency is 0.63, I just take the reciprocal of that. And apparently it is. If I use the unrounded version, it's something more like that, I guess. I guess we could change that to just to be consistent. And then if you go with this equation, you're going back to all original given values, where you're just using this other form of the velocity equation. Either way, you're going to get, that's not right though. That should be F, and this should be hertz. There we go. Get the same answer either way. And then for part C, what's the acceleration? So now we're back to the same thing we were doing before. V squared over r, both of those values were given. And so we can find that it's going to be about 2,500 meters per second squared. And this, again, makes sense. We got a large acceleration because it's 500 kilograms. It's a pretty big object. And it's moving 250 meters per second. So that's fast. Questions? All right. So for this worksheet, I just wanted to give you a chance to practice getting comfortable with these equations, practice getting comfortable with the units, and you will not be asked by College Board to just solve something quite this simple. Okay, they're not gonna give you that information to say, hey, find the period, find the frequency. But you will frequently, no pun intended, have to find some of those things as a step in a larger problem. So I just want you to get pretty comfortable with those equations. All right. Next up, we're gonna take some notes. Like I said, this will be a lot of review, probably not a whole lot to write down this time, but one new equation and just sort of turning our thoughts toward forces, but still connecting to all the kinematics things we talked about last time. Let me get back to sharing that screen. All right. So last time we were focused on kinematics, and today we're going to focus on the dynamics. And dynamics in some books just means basically applying forces to change the motion of something. So you'll sometimes hear physics divided into two categories of statics versus dynamics. Statics being things that are at rest or in constant motion, and dynamics being things that are accelerating. And if something's accelerating, it has to have a force. And so that's where that term comes from. And for something moving in a circle, we know that if it's moving in a circle, there has to be a force, because otherwise it would go in a straight line according to Newton's first law. Could I get someone on the Zoom to read this slide for us?
Sure. Dynamics of uniform circular motion. For an object to be in uniform circular motion, there must be a net force acting on it. We already know the acceleration, so we can write the force in the equation.
And with that,
should I read the equation?
That's okay. You can all see it. So in the equation, we can see acceleration we found last time was v squared over r. You just use that multiple times on the worksheet. If we multiply that times the mass, that will tell us the centripetal force. That's the force, for instance, in the string that's making the stopper turn. If we're going back to that demo that I did last time. This is the one equation that's new today. And it's really just Newton's second law, but just like we adjusted Newton's second law to find weight, and we said, well, Newton's second law could be adjusted to be mg to find the weight of something. Now we're saying Newton's second law can be adjusted to find the centripetal force of something moving in a circle. And it's just going to be mv squared over r. It's just substituting something equivalent for a. And this v squared over r, remember, only works if it's moving in a circle, uniform circular motion. You would never use v squared over r if it's moving in a linear pattern. So it is limited to centripetal acceleration, but in this problem, we're trying to find centripetal force. All right, so we can see the force must be inward. So this is something we talked about last time. If we think about that ball on a string or stopper on a string, we talked about how it's the tension in that string that keeps the ball turning. If the string breaks, it will no longer turn, right? So we've talked about that last time. Could I get someone in the room to read this one for us?
Yeah, imagine the direction that a ball swinging in a circle on a string is actually moving at any point in time. If you were to cut the string, the ball would keep moving straight out of the circular path. This direction of the velocity is actually perpendicular to the radius of the circle, the string, and it is said to be the tangent. It is said to be tangent to the circle.
All right, so again, things we talked about yesterday, but now sort of tying it into the force instead of just thinking about the kinematics purely. So this acceleration that's, this force that's causing the acceleration is perpendicular to the tangent velocity of the object's movement. And again, nothing really new here, but just tying some things together from last lesson to this lesson. All right, can I get someone in the Zoom to read through this slide for us?
Sure. The string is actually pulling toward the center of the circle no matter what point you look at. Remember, strings and ropes can only pull, they cannot push. This string is applying a force toward the center, so there must be an acceleration toward the center of the circle.
All right. So again, we're drawing conclusions, we're summarizing things, we're tying in what we learned last time to now the concept of force. So that string tension is the force that creates the acceleration, both because the tension is the net force, then that has to be the same direction as the acceleration. The net force direction and acceleration direction are always the same. All right, and then here's a nice little summary kind of review basically of the lesson from last time, back to kinematics. The acceleration is called the centripetal or radial acceleration, like we learned last time. Its direction is always towards the center of the circle. We can calculate it by taking v squared over r, where v is the tangential velocity and r is the radius of the circle. So we may have even had this almost identical slide last time. We just want to tack that back in there to remind you that we did learn this equation, and it is the acceleration that the force generates. And we know how to calculate it. And also, again, reminding you that it is called centripetal. Now, some books do refer to it as radial acceleration, but I've never heard it called radial force. So generally, you'll see centripetal acceleration and centripetal force. All right, the last two slides, before we get to some question slides, the last two slides of quote unquote notes are going to talk about a force that actually doesn't exist, a fictional force, so to speak. You've probably heard of centrifugal force. If you've ever been to like a fair where they have one of those rides, sometimes they even call the ride the centrifuge, where you stand against a wall and it spins and you stick to the wall and the floor drops out. Or if you've been in a biotech class or a chemistry class, you may have used a centrifuge. Or if you know about how they separate blood components, they use a centrifuge. But that word centrifugal force is a misnomer. There is no such thing as centrifugal force. All right, so let's learn what's really going on. Could I get someone in the room to read this one for us?
I can't.
Okay.
Dynamics of uniform circular motion. There is no centrifugal force pointing outward. However, the natural tendency of an object to move in a straight line, inertia, must be overcome to make it go in a circle. If the centripetal force vanishes, the object flies off to the circle, off tangent to the circle.
And then on the side there, they're showing you if the string breaks, this is what happens. The object goes straight, tangent to the circle from that point. The bottom picture shows you what does not happen. It does not curve. It does not curve either direction. It's going to go straight. There's no outward force that's going to make it curve away from the center of the circle. The force will only turn it back to the center of the circle. So centrifugal, actually, if I remember correctly, means center fleeing. We talked about centripetal meaning center seeking. Well, they are opposite of each other, but centrifugal force doesn't really exist. It's just the inertia an object has. So if you think about the ride, the centrifuge ride where you're standing against a wall and it's spinning, well, the friction between you and the wall is making you spin, and the floor underneath your feet, the friction holding your feet steady on the floor makes you spin. And so as you start to spin, your body starts to accelerate, and your body naturally then wants to accelerate in a straight line. But the wall keeps pushing you to the middle so that you can't go in a straight line. And so it forces your body to travel in this central movement, and the wall is pushing against your back to keep you going in a circular path instead of going in a straight line. So, and it's just the friction between you and the wall that keeps you against the wall when the floor starts to drop out. If you're in a car turning around a curve, the curve to the left, you feel thrown to the right. Correct? Like curves to the left, you feel like you're being thrown to the right. And so we think, oh, there's a force pushing me to the right. No, the car's turning out from underneath you. You want to go straight. The car's turning left. So you feel like you're going right because your body's trying to go straight. Right? So it's your inertia. There's no extra force. There's no outward pushing force. There's only the inward pulling force. And it's the seat belt and the car door and the friction between your backside and the seat underneath you that keep you from flying out with your straight inertia. So if this was a car and it was purely open and it was a frictionless seat with no seat belts and no walls or doors or anything, as we're going this way and we turn, I just keep going that way. So it looks like I went out the right side of the car, but I just kept going straight. The car just turned out from underneath me. So there's no force making me go outward. It's a sort of an illusion, so to speak, because it's just our inertia that wants us to keep going straight. And inertia is not a force. Inertia is just a property that matter has based on its mass. The more mass it has, the more inertia it has. All right. Last slide of content here. Can you get someone in the Zoom to read this last one for us?
Sure. A centrifuge works by spinning very fast. This means there must be a very large centripetal force. The object at A would go into a straight line except for this force. Due to the center-seeking force, it winds up at position B.
So the test tubes in the centrifuge are what are getting pulled to the center. And otherwise, the test tubes would fly up across the room, right? So there's a casing that keeps the test tube from flying across the room and forces it to go into the center. And so it's the test tubes that are experiencing that centripetal force. Now, the objects in the test tube, they have inertia. So as they start to move sideways and the test tube turns, now they can't keep going straight like they want to. So they just keep getting pushed against the bottom of the test tube by their own inertia. So the centripetal force turns the test tubes, and the inertia of the objects cause them to settle into the bottom of the test tube. The more mass they have, the more inertia. The more inertia they have, the further down the test tube they separate. So this is why they separate out blood components, because the platelets and the blood cells and the plasma all have different densities, and so they separate at different depths in the test tube, because the ones with most mass have most inertia, and they end up at the bottom. But it's their inertia that forces them to the bottom, not a centrifugal force. So we shouldn't really call it a centrifuge. We should call it a centipede, right? Or an inertia machine, something, I don't know. But there's no such thing as centrifugal force.
Could you call it centrifugal inertia?
I suppose so.
Okay.
Yeah, I mean, it's just, but usually we hear it called centrifugal force.
Right.
Yeah, and it's not really fleeing the center either, even as inertia, because the inertia is always going to be straight. Yeah, so it's tangent to the circle. So I would just try to avoid using centrifugal, probably a safer bet. All right, so here's a couple questions to wrap up before we practice some other things. So when an object experiences uniform circular motion, the direction of the net force would be A, in the same direction as the motion of the object, B, in the opposite direction of the motion of the object, C, directed towards the center of the circular path, or D, directed away from the center of the circular path. So go ahead and put your answers in the chat if you're on the Zoom, A, B, C, or D. Not seeing any answers. Maybe it's delayed, or you're just still thinking. Okay, here they start to come. Yay. All right, so now there's a bunch of them, and so far on the screen, they all say C. Jack, do you agree with C?
Yeah, I was gonna say C.
Yes, that is correct. So if something's moving in a circle, the force that causes that, the net force, is towards the center of the circle. Therefore, oops, just got a bunch of stuff on here that's giving away the answer. All right, so
Guys, I think it's
if you can't answer that one, you may have a problem. But let's talk it through since I gave it away here. And this is, I don't know why these boys and girls keep wanting to spin things above their heads, but this boy's whirling a toy at the end of a string around his head. I don't know, I didn't seem to do that when I was a kid, but the string makes one complete revolution every second. So the period is 1. He keeps the radius constant, but decreases the speed so that the string makes one revolution every 2 seconds. So now the period is 2. What happens to the tension in the string? So you've seen the answer because it was circled. But I want to see if we can make sure we understand how that answer is true. So if we go back to the force equation we learned today. Oops, that kind of looks like a V. There we go, that's better. It says here that they are keeping, the boy is keeping the radius constant, so that stays the same, and the object of the toy's mass would not change. Now, there is something, if you watch those videos on YouTube or not on YouTube, on the AP Classroom, then I believe in one of them, he mentioned the rule of ones, Greg Jacobs. And so I want to illustrate that in case you didn't see it yet or didn't make sense, or I'm daydreaming and it was in a different video, because I've watched a ton of them. But we're trying to figure out what happens to the tension, what happens to this force. And the rule of ones is just a strategy he's made up to help you kind of think through the probability. In this situation, the toy's mass is not going to change. So we would substitute a 1 in because it's not going to change. And then we know the radius. It says the radius is constant. So we know that's not changing. If that's not changing, we put a 1 in for that as well. All right, so we just put ones in for the things that aren't changing. And then we're going to put a factor in for the thing that is changing. So it says it had a period of 1 second before. Now it has a period of 2 seconds. So what's happening to the velocity?
It's 1.5.
Yeah, the velocity is now 1/2 what it used to be. And in this equation, velocity is squared. So now we put ones in for the things that aren't changing. We put the factor of change in for the thing that is. And now we know the force would be changed by 1/4 or cut by 1/4. So that factor, that rule of ones that he called it, may be helpful for you in these proportional kinds of questions. All right, so I'm gonna have to do a quick change here. This is like a costume change or something. So I'm freezing that so you can't see. I'm stopping the share so they can't see. And then I gotta fix this real quick because I think I forgot to. Yep, I
Do it
did.
for all of them.
There's only 2, but these last 2 I have it highlighted. So I want you to actually figure this one out instead of being told the answer. So now it's clear. Little technical difficulties here, or maybe it's just old age forgetfulness. There you go. So this is your last practice question here, and this is a kind of question, multiple correct, that is common on the AP exam. So for each of the following, 2 of these suggested answers will be correct, and we're just going to look at one of them today. But we'll be increasing the frequency, pun intended, of these kind of questions, because there's always 3 to 5 of them at the end of the multiple choice section on the exam. So I want you to get used to thinking them through. All right, an object is moving in uniform circular motion with a mass m, a speed v, and a radius r. Which of the following will quadruple the centripetal force on the object? So think it through. There's 2 that are correct. Once you've identified those 2, you can put them in the chat if you're in the Zoom room. And then I'm going to call on you guys and see what you think and see if you agree with what the Zoom folks believe. Depending on how good your eyesight is, you might be able to see what's coming up there on the screen. It's pretty small, but you're seeing what some of them are voting for. It's been a pretty good agreement. Almost everybody's come up with the same 2. So Evan, what do you think? What did you determine?
I thought it was A and D.
Okay, can you tell us how you came up with that?
Well, doubling the speed is squared. So if you double it, then it is actually quadrupling it. So it would quadruple the force. And D, because if you cut down the radius to 1/4, it's a reciprocal relationship or something.
Mhm.
So it actually would quadruple the force rather than 1/4ing it.
Quartering it, yeah.
Yeah.
Good. Yeah, so since the radius is in the denominator, it's reciprocal or inverse related. And so if it's 1/4, then the force will be 4 times. Very good. So it should be A and D. All right, and we'll continue to practice some of those throughout the semester to get you more and more confident at those kinds of questions. All right, now the last thing we're going to do is, well, 2 things actually, but they go hand in hand. We're going to actually walk out to the mezzanine and do a demonstration with a bowling ball. And then we're going to have you work in groups on worksheet 1 to try to get at least a few questions figured out. Not an assignment, just practice thinking about forces and how we draw free body diagrams now that objects are moving in circles. Okay, but we're going to go try to visualize it by going outside. So I need you guys to help. If one of you can prop the door open, and if one of you can get the hammer here, I'll get the bowling ball. Yeah.
Guys, good job. Just the door stop.
Yeah.
That's a fancy door stop. The next one.
Start video. Stop share. All right, can you guys on the Zoom hear me okay now? All
Yes.
right, we're just out on the mezzanine, so I'll give you a quick look. We're just up above Mr. Gillis-Smith's class down there. It looks like Mr. Velasquez is actually teaching, must be aerospace. All right, so what I've done is I've just taped off a path here, and it's got obviously these 2 straight legs and then a circular path at the end. And so what we're going to have these guys do is your goal is to, using the mallet, you're going to hammer the bowling ball. So you can't just push it with the mallet, you got to hammer it. Okay. And you have to try to follow the path as closely as you can. Okay. So Evan's going to go first, and we're going to see how successful. This might become an Olympic event. So this is potentially training for them.
Are you allowed to let it stop?
Ideally, you want to keep it moving if you can. Yeah, it's kind of a race. All right, nicely done. So before we have somebody else go, sometimes it's easier actually for the people watching to figure out what's going on than it is for the people doing it. So let me ask Evan first. What did you notice you had to do differently when it was going around the circle? Okay, so you actually, and here we can let Ian's or Evan's face show. So yeah, you were hitting it towards the center, and I don't know if you could see it on the video. I think you guys could probably see it. He frequently was having to tap it almost directly into the center, right? Okay, Ethan, let's see if you can beat Evan's speed. All right, nicely done. So did you feel the same thing, that you had to hit it one way to make it move forward and the outside to make it curve?
Along the circle to make it go, and then hitting it outside will keep it in the circle.
All right.
Slow it down a little.
All right, good. Okay, Jack, your turn. Yeah, that was nice, smooth second half there. All right, good. Let's go ahead and head back in the room and we'll discuss this.
I don't know, I think it's 50 bricks.
Oh, it's big hand.
All right.
What is going on with this bowling ball?
Yeah, that bowling ball was donated. It's probably seen better days.
You have very large hands.
All right. So hopefully you guys on the video could see it well enough to kind of see the angle that the mallet had to be applied, the force with the mallet had to be applied to get it to turn that curve. I don't know how long that circular path's going to last out there. It's just blue tape. So as people walk on it, it's going to get torn up. But we'll leave it up there. So if students come in these next class days, whether you have class or not, if you want to come up and see if you can, break the new world record, train for the next Olympic event, you're welcome to come up and try it. We got the stuff set ready for you. But what I'm hoping that you recognized is to make it curve, you actually did have to hit it on the outside towards the center, right? You had to hit it one way to make it move, but you had to hit it on the outside towards the center to make it curve, and that is the centripetal force. So if you guys haven't picked up the worksheets, go ahead and do so. We're going to be focusing on worksheet 1, but 2, 3, and 4 is what we're doing next week. So if you want to grab copies today, you can. And then for those of you in Zoom, if you haven't opened up or printed or found worksheet 1, it's in unit 7. So make sure you're getting worksheet 1 opened up and ready to go.
That's all. You have a hole puncher?
Yeah, back there somewhere on that table, there's all kinds of office supplies. All right, we're going to take about 10 or 12 minutes, so not a huge amount of time, to see if you can get the first 3 or 4 questions figured out on this worksheet. Now, the first question is actually about what we just witnessed. It's slightly different. It says a bowling ball is rolling down the hallway, so it's already rolling. You guys had to make it start, but if it was already rolling down the hallway, what would you have to do to make it follow a curved path? And then it asks you to try to figure out how to draw the free body diagram. Now, this worksheet, like a lot of the worksheets, they just call it force diagram, but I would like you to use actually free body diagrams instead. And then in those free body diagrams, you'll probably want to think about looking at it from the side. Okay, so not looking at the ball from above, but looking at the ball from the side. Okay, that will be your best option. Yeah, that's fine, Kate. So what we'll do is you guys will just kind of work and converse and discuss it. You got to stay socially distanced, but you can still talk about it and compare answers and compare your results. And then for you guys in Zoom, we'll put you in a couple of breakout groups. So you'll have 3 in a group, and you'll just also be kind of working on it, discussing it, help, kind of, hey, what did you get? What does yours look like? And discussing it. Like I said, it's only going to be about 10, 12 minutes max. So you'll hopefully be able to get the first 2 completely finished, and maybe 3, maybe 4. We're going to continue to wrap this worksheet up on Monday. So this is not assigned. You don't need to work on this as an assignment, but I want to see how much of it you can get done in these small groups. So let me go ahead and create the groups. All right, so one group will have 4 and the other group will have 3. All right, if you have questions, you can click on the button to ask me to come in, and obviously you guys can ask questions because I'm just here in the same room. So good luck.
Is this sort of the same like shape is out there?
Just making it curve, not necessarily the same
Oh.
shape. This.
Are we working together?
Yeah, so for A, I just did like a ball, and then I drew like a dotted line for the curve, and then I just drew like an arrow with a hammer, like hitting it inwards to keep it going.
Yeah.
Because if it's going this way, you have to hit it around inside
So
the,
you always want to hit it like perpendicular to the force.
yeah.
Going to the right, right?
Mhm.
Yeah.
Yeah. And then,
While you're curving the ball's path, are the forces on the ball balanced? No.
yeah, they can't be balanced if you're moving. If you're
Wait, how do you draw a force diagram?
Free body diagram. So the ball would be the
Towards
dot.
The center.
Mhm.
And
So
you
that's what I
said,
was saying, looking at it from the side.
Oh, okay, so
Like if you were watching the ball go around the curve and you're looking at it from the side as it's kind of curving in front of you.
Oh.
what point in time is the free body diagram for?
Yeah.
At any instant.
Okay.
Yeah.
Yeah, you need gravity, right? Yeah. And the force, those still exist.
if it's going,
To the right.
yeah, if we're just gonna base it off
Yeah.
of the last
Right
one.
force.
Force.
Force hand. Inch. Is it all accelerating? Yes. And the direction is changing. Magnitude. Airplane banks and makes a wide circle. Draw a force diagram for a head-on view.
So. Head on view.
Do you want FT for thrust or F?
Uh,
for
you can-
lift?
You can use whatever you want.
Okay. I think it's lift somewhere.
We usually use T for tension, but you could
Oh,
use
right.
T for thrust too. In the context of the question, I think it's clear enough.
Yeah. Oh, and it's not really thrust, it's lift, so I'll just do an L.
Name the force.
I think it's just the lift force
Yeah, lift.
of the plane's wings.
And then for number one on C, sorry, I missed that. Is it, is the ball accelerating? If so, what is changing with the velocity?
I said yes, the direction's changing. Oh, circular current. Name the force, the interaction between objects that allows the car to travel in a circle. In what direction does the force push on the car? Draw a diagram for the car as it approaches head on. Well, centrifugal, I think it wants the centripetal force. Is what it's asking.
Oh.
That might be what the last question was asking
Yes.
too.
Just so you know, I'll give you a little spoiler. I like better what you had first than centripetal. And here's why. Centripetal is very generic. It's anything that makes it go in a circle. Could be friction, could be air
Okay.
resistance, could be gravity, could be tension in a string. So I like the more specific force descriptions you were giving better. And then it is a centripetal force. It's not wrong. So it's not wrong to put that. But I like the more specific examples you gave better. And then recognizing, oh, that very specific thing is what's the centripetal force. The centripetal force is just generic.
Yeah. All right, so we'll just slap centripetal in front of everything.
Yeah.
Centripetal friction force, the centripetal lift force.
Right. Because if it's friction force, the advantage is you have a formula for friction. You
That's
times that
true.
in. And if it's, but there's no like, there is a formula for centripetal force too, but you may not know the velocity and the radius. But if you know it's friction that's causing it, you might be able to know the coefficient of friction in the normal force, because the normal force is probably just the weight,
Right.
right? So if you call it the more specific name, you often have an equation like, oh, it's gravity. Oh, there's a formula for gravity.
Mhm.
Yeah.
Would it be towards the center of the turn?
Yeah. Does it say which direction it's going? No.
No, probably just. Now that I've seen that first one of it saying going right in a circle every time I imagine it, I'm
Yeah.
thinking it's just going like this.
Describe the motion of the car if the force you described in part A suddenly vanished. It just go straight.
The car would slip. It's like when you hit ice.
So it would continue in whatever tangential direction it was going.
Yes.
The 35 meter radius turn is level. The car has a mass of 1,200 kilograms and the coefficient of friction between the tires and the road is 0.85. What is the maximum speed the car can travel through the turn? That's a lot of questions.
All right, no, should we use 10 for
Gravity?
yeah.
Um,
Yeah, it's
you
easy.
should probably use 9.8.
All right, fine.
Just so that we have two sig figs. The sig figs are kind of infuriating. You do all this work and it's like this long decimal line. Yes, and it's shrunk down to a single number.
If you use 9.8 or 10, they would still accept 2 sig figs. So
Huh.
it's not mathematically best to do that, but that's just college boards like wiggle room. So you can use 10 and still, they just basically are saying you're sort of considering G to be constant, even though we know in reality it's not. And so if you're saying it's a constant, you can ignore it for sig figs and you just look at the other values. So if you use 9.8 or 10, just focus on the other numbers that you use to determine sig figs.
10 it is then. So we should probably figure out the centripetal force first, and then the friction force, and then or the maximum friction force. It's static friction, right?
Yeah.
Yeah, it's not sliding.
What time does this class get out? Is it 11:25?
Yeah.
Okay.
So the maximum is 1,020. So yeah,
Oh, I need to do that.
and then we just put that into the
Yeah, because it'd
other
be,
equation.
yeah, 12,000 times. Oh yeah, then you could use that as the force. It's over 10. Yeah. You got 10,200.
I got 1,020. Wait. Oh, I forgot.
Did you multiply by 10 for gravity?
Almost.
Alright.
I added a zero. It's okay.
Wait. Oh, wait, oh no, wait, never mind. Yes. You would just need the acceleration due to gravity times the coefficient of friction is the acceleration that the car can experience, because you multiply by the mass of the car, but then you divide by it again
Yeah.
just to get the acceleration.
Yeah, so technically, it's just the. Oh,
So it's just 8.5 is the maximum acceleration.
yeah, because you're just multiplying this side by mass and this side by mass to get the force.
And then you divide it away.
Yeah, so it's no.
Yeah, all right, so 8.5 meters per second squared equals v squared over. Wait, no more.
I got 17.
17.
Yeah. Which makes very.
I got 0.5 to 0.49 meters per second.
Check. Wait, did you set it up? Get this one, set it up. Or did you set it in?
No. So I did that times the coefficient of friction equals that, and then I divided by the mass of the car.
All right, yeah, I figured it out.
You got 0.5 for the final velocity.
Yeah, 0.49.
Yeah.
What did you say you got, Evan?
Okay, wait, really quickly, I
You got
can do
17?
from,
You got 7?
I can,
Wait.
like, when I had this, I can do that, but how did you get to? acceleration?
So you have the
Wait a second.
normal force times the coefficient of friction.
All right, so we've had some good conversations going on in this room. Hopefully you guys had some good conversations going on in your breakout rooms. We're just gonna take a few minutes and try to go through the first couple of questions. I don't know how far we'll get,
But then you have to divide by the kilograms.
letting these guys try to wrap up their conversation here on number 3. How many of you were able to solve for the velocity at number 3?
The car could experience.
David, how many of you got that far?
1,200 kilograms to get the max acceleration the car could experience.
Nobody finished that one up.
And that car
That's what they're
8.5
trying to finish up right now. I think I'm gonna have to interrupt enough.
Yeah, okay, I got that, thank you.
All right, so
I got 17.
Wait.
Because I took that maximum, I put it into the close equation.
Oh.
I divided by the radius. Wait, no, I multiplied by the radius, divided by the.
they're still wrestling with 3, trying to figure out that velocity.
Oh, I might have divided instead of multiplying. Yeah, I divided instead of multiplying.
So like, how did he get this thing? Did you
No,
guys-
well, I just used the 8.5 that he got, once I got it.
But you divided instead of multiplying too, that
For which one?
for the last part.
For
Yeah, it's
8.5.
17.2.
All right, so real quick, for you guys here and you guys there, we got
8.5 divided by.
great conversation.
Yeah.
This is where if we were all in one room, it makes things a lot easier. But we'll keep doing the best we can. Anyway, I want to make sure that I don't forget to tell you again that the assignment is not this worksheet. This worksheet is something we're going to continue to work on in class. The assignment is to go to the Gizmo website linked on bulletin board page of Access. And if you go to our class, you'll find the uniform circular motion. If for some reason you can't get into our class, just go to the site and Google, or not Google, search on the site, uniform circular motion, you'll find it. Open up the student exploration sheet, just like we've done before. You don't necessarily have to answer the assessment questions that are on the website, but you do need to complete the student exploration sheet. And so that's your assignment actually. I'm gonna stop sharing that though for a minute so we can take a look at some answers for this. And we'll probably just get through the first 2 questions today. And we'll come around to number 3 next time. Because I don't think we can get all 3 of those done in the short time we have left. But let's take a look at what we can for number 1 and number 2. So for number 1, this is very similar to what we witnessed out in the mezzanine, that the ball initially they had to make it go in a straight line, but then to make it start to curve, they had to change the force that they applied. They actually had to start making it go the other way in the curve. So been interesting if it matched more like this one, but to make the ball curve, you have to be applying a force that pushes it back to the center. And so your picture doesn't have to look exactly like this, but the goal is that to make it go to the center, the force has to be pushing to the center. So something along those lines for part A. While you are curving the ball's path, are the forces on the ball balanced? Draw a free body diagram. It says force diagram, but I always translate that to mean free body diagram. The forces would not be balanced because if it's moving in a circle, there is an acceleration. That's part of uniform circular motion. It has to have an acceleration because the velocity is changing. The velocity is changing in its direction. But if we look at the ball from the side, the ball has weight downward, and the floor provides a normal force upward, and those would be balanced because the ball doesn't rise or fall. But there is that net force to the side. Now, how you draw it on your paper just depends on where the center of the circle is or whatever in terms of which way that points, but just showing that it would be perpendicular to those other two forces, right? Because it's going to be parallel to the ground. And that it's only one force. There's not an opposing force in the other direction. So remember, we don't add velocity to a free body diagram. We're only looking at the forces. So you should just have three: the normal force, the weight force, and then the pushing force that makes it curve. And then, is the ball accelerating? If so, what is changing about the velocity? And that's what we talked about in today's lesson and somewhat in the last one, that it's the direction that's changing. Velocity is a vector, so it has both magnitude and direction. And therefore, the direction changing means it is accelerating, even if its speed is constant. Questions on number 1? All right, number 2, an airplane banks and makes a wide circle. Draw the free body diagram for a head-on view of the banking plane. So they gave you kind of a clip art of the plane to help you imagine what it might look like if it's banking. And what we're saying is, I don't know if you can see my hand in the video or not, but it's banking in a horizontal circle, right? It's angling so that it curves in a horizontal circle. And so we know that the plane still has weight. It would fall if there were no other forces, it would fall to the ground. So, but there are other forces, and if it's banking, then the air is going to be pushing on the underneath side of those wings. And if the wings are angled, then that force has to be angled to match the wings. So anytime there's an angled force, we want to think about the components. And the question B says, name the force that allows the plane to travel in a circle. So as the plane starts to bank, they're generating a horizontal component for that lift. And that horizontal component is going to push the plane to the center of a circle. And so the more they bank, the greater, as they change the angle of the bank, they can adjust how much of the angle is gaining horizontal and how much of it's vertical. Now, what would have to be true if the plane's keeping constant altitude? What would have to be true about the vertical component?
Have to stay the same.
Have to stay the same and?
Be equal to the force of gravity.
Yeah, equal to the force of gravity or equal to the weight. So in this kind of a problem, one thing we might recognize is, okay, let's say the problem said the plane banks at a 30-degree angle. Well, and it maintains its altitude. If it maintains its altitude, the vertical component is the weight. So now you know one side of that triangle. And if you know the angle's 30, you can use trig and figure out what that horizontal force is. And we had a good discussion in here that I want you guys to make sure you hear as well. They were discussing, should we call it the lift force or should we call it the centripetal force? Well, I would call this the lift force, or the force that the air is pushing against the wings. And then the horizontal component would be what's actually creating the centripetal force. While the vertical component is actually truly creating the lift to counteract the weight, right? Now, the names aren't as important, but another thing that I mentioned is that centripetal force is generic. We have an equation for it, mv squared over r, but if it's friction, we also have mu Fn. If it's gravity, We also have capital G M1 M2 over R squared. If it's a spring, we also have Kx, right? So I would call the centripetal force what it actually is: friction or air resistance or gravity or tension in a string. I would call it whatever it is and just recognize that it is also a centripetal force, but recognize the centripetal force is not a unique kind of force. It's any kind of force that makes something go in a circle, whether that's tension, friction, gravity. It's very generic. Okay, so just keep that in mind. That will help you, I think, at times not get confused. A lot of times students will say, oh, there's a friction force. And then they'll say, oh, but there's a centripetal force. And they think it's two separate things. And it's actually this, that the friction force is the centripetal force. It's the friction that makes the car spin or makes the car turn. So it's not a separate thing. The centripetal force is caused by something else that we know: tension, gravity, whatever. All right, that is good for the day. And we have a few minutes left. So if you guys in the classroom want to experiment with the flying pig, or if you haven't picked up the other worksheets, or if you have questions for me, that's fine. For you guys in the Zoom, if you have questions for me, then feel free to stick around and ask those questions. Remember, this worksheet is not your assignment. The Gizmo on uniform circular motion is. And if you don't have any questions for me, I would appreciate, I want to let you know this too. There's a chance I won't be physically here next week. I might have to be teaching remotely. My wife last night found out that her father probably has a few days to live. And so we're trying to figure out if she's gonna go or we're both gonna go. They live in Indiana. So if we end up both going, I'll probably still be able to teach the classes, but I'll be doing it from there instead of from here. So for those of you that'll be coming on campus, I just wanted to let you know that's maybe happening. And I would appreciate prayers for my wife's family, especially as they go through this time. So, but yeah, like I said, the Gizmo is the assignment. So that's the thing I wanted to make sure you knew about too. All right, it's good to see you guys. If I don't see you between now and the weekend, enjoy the rest of your week and enjoy your weekend.
Thank you.
Thank you.
Thank you.